So we're going to talk about invariants and semi-invariants or mono-invariants this week. And we'll start off with invariants and do a few problems, and then semi-invariants, which are kind of a more general form, and we'll do one problem on those. So an invariant is basically a function of some problem setup. And the problem setup changes under some transformation, but the invariant is some way of measuring what that setup looks like that doesn't change when you apply the transformation. So we say that the invariant is invariant under the transformation or with respect to the transformation in the context of the configurations that we're looking at. So if you know that the invariant doesn't change when you apply the transformation, that lets you say something about whether applying the transformation to G can get you to some other state of the system. So we'll see a few examples of this in the questions. But the key thing to realize is that whenever you're asking a question about can this system move from state A to state B, an invariant can help you show that it can't, but it can't actually help you show that it can. If you want to show that it can, the best way to do that is usually to construct some valid transformation from A to B. So we'll start off with our first problem, which is a graph theory problem. So the first thing that requires explaining here is what a planar graph is. This graph on the bottom left is not planar because you can't draw it without having lines crossing each other when you draw it on a flat surface. Whereas the one to the right of it, it is planar because you can draw it on a flat surface without any intersecting edges. And this question is telling us that there's this invariant of planar graphs, where any planar graph, if you take the vertices minus the edges plus the number of regions or faces that the graph divides the plane into, then you'll get a constant. And the transformation here is really moving between any two graphs, A and B, but we'll prove that this is an invariant in a particular way. So for whatever graph you have, take one of the vertices and make a copy of it in a new plane P. And you'll notice that if you have a plane with just one vertex in it, then you have one vertex, 0 edges, and one face. And if you compute the invariant V minus E plus F, you'll get 2. Now we want to build up from this one vertex to a more complex graph. And eventually we'll build up from this one vertex into the original graph. And by showing that V minus E plus F is invariant at each step of that process, we can show that it's the same for the final graph as it is for the initial graph. So because the original graph is connected, that's part of the problem setup. From this one vertex that we're copying, we can get to any other vertex just by chaining on vertices to this first one. So we'll take V1 and we'll create all the nodes around it that are connected to it in the original graph. And we'll draw connections to those. And you can see that whenever you add a leaf to this tree, you're going to have one more vertex, one more edge, and you're not going to have any more regions because you're not splitting the plane at all. So under this particular transformation, v minus e plus f is invariant. So we can get all the nodes in the original graph using this, but we can't necessarily get all the edges. And one technical detail here is that all the edges that you use to create these new nodes in the copy have to be valid edges in the original graph. And we're still able to get all the nodes because the original graph is connected. And in fact, if it's not connected, this equation is not actually invariant. So now we want to complete the copy by adding in all the edges that we haven't yet copied over. And when you add a new edge without adding any new vertices, the number of vertices changes by 0. The number of edges increases by 1. And the number of faces also increases by 1 because you're taking an existing face and cutting it in two with an edge. If I can annotate this here. If I have these 3 connected vertices here, you'll notice that there's 3 vertices, 2 edges, and 1 region. So we have 3 minus 2 plus 1, which is 2. And now if we add another edge here, we introduce a new region by cutting the region we had before in half. And we also introduce another edge. So it's invariant under that transformation that we're doing in this graph. And you can do the same here, same thing here again. And it's all invariant. So that's good. And now that we have a copy of the original graph, and we use those 2 different transformations that we know the formula, the expression was invariant under, we know that at each step of the way, v minus e plus f stayed the same. So for the final graph, the final copy of the original graph, we have the same v minus e plus f value as we had to begin with, and we just copy one vertex over. So that's the proof.
All right, so yeah, I'm doing this question. Okay, so this question is a tiling question. So we've got a 66 by 62 rectangle, and question is, can we tile it with 12 times 11 rectangles? And so you can make the tiles vertical or horizontal. And yeah, the question is whether you can tile it with 12 times 11 rectangles. All right, so for this question, you can play around a bit, and since 66 and 62 are quite large numbers, it might be useful to consider smaller cases before moving on to larger cases. So let's see. All right, so before we go on to the first dot point, yeah, what we first see is every tile is 12 by 1, which means that there's 12 squares in every 12 by 1 rectangle. So if you can tile a rectangle with 12 by 1 rectangles, the total number of squares in your rectangle has to be divisible by 12. So in the large rectangle, the total number of squares has to be divisible by 12. And the question is whether this is divisible by 12. And you can see this is divisible by 66, and 62 is divisible by 2. So 66 times 62 is divisible by 12. So it means that since it's divisible by 12, it doesn't rule out the possibility of 66 times 62 rectangle being possible to be tiled. So it doesn't rule it out, but it might be still something that makes it impossible to tile it. So you could say that divisibility by 12 it's one condition for the large rectangle to be possible to tile, but it's might not be enough conditions. So an example would be 3 times 4. So 3 times 4, that is going to that's going to be divisible by 12. So 3 times 4 is 12 squares. However, you can't fit a 12 by 1 rectangle in a 3 by 4 square, 3 by 4 rectangle. So it's impossible to tile a 3 by 4 square. So you could try other small cases such as, let's say 6 by 8. So 6 by 8, that is also divisible by 12. However, you still can't fit a 12 by 1 rectangle in there. And you can go even higher. For example, you could do 16 by 9. So 16 times 9 is 144, and that's divisible by 12. However, you still can't tile it with 12 times 1 rectangles if you try it out. Okay, but what can you tile with 12 by 1 rectangles? So one obvious example is if you just lay all the tiles horizontally. So if you lay all the tiles horizontally, you can tile anything that has, you can also tile like this. So you can make every single tile horizontal. The horizontal axis, or look at the horizontal side, and you'll have a multiple of 12 number of squares on the horizontal side, and you can have any number on this vertical side. So you can tile 12m by n. So you can tile 12m by anything, rectangles using 12 by times 1 rectangles. So that's an example of something you can tile with 12 by 1 rectangles. But the question is this type of large rectangle, the only rectangle you can tile with 12 by 1 rectangles. So that's what we have to investigate. So yeah, we can go to the next slide, next dot point. Okay, so what we'll do is we'll conjecture that the 12m by n large rectangles are the only large rectangles you can tile with 12 by 1s. So we will try to prove that it's impossible to tile the 66 by 62. So here we're using a proof by contradiction. So a direct proof is pretty hard in this case because it's hard to directly prove that you can't tile this. So we'll do contradiction where we assume that you can tile a 66 by 62 rectangle. Okay, so now we're doing something called the coloring of this whole rectangle, or you can also call it a numbering in this case. So giving every square a number from 1 to 12. So using the fact that there's a 12 here in this question, what we'll do is we'll number every unit square a number from 1 to 12, and it follows a certain pattern. So the pattern is if you go down the column, you go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and after 12 you go back to 1 and count again, so on. So you can go in a loop. So you go from 1 to 12, and after 12 you go back to 1. So that happens in each column. So every column, if you go down, it's going to cycle from 1 to 12 and back to 1 again. Let's say now we're going, if you go right, let's look at the first row and go right. What we see is we have 1 here, and the number before 1, if you loop back, is 12. And if you loop back again, it's 11, 10, 9, 8, 7, 6, and so on, back to 1 and back to 12 and so on. So that's the pattern of this numbering. Okay, and as we said earlier, dot point number 2 is the area of this rectangle must be divisible by 12, and we confirmed it. 66 times 62 rectangle has area divisible by 12. So that doesn't really help us prove that it's impossible. So we need some more information to prove that this is impossible to tile. So you can go to the next. Okay. So from earlier we did some experimenting with smaller m by n rectangles. So we tested where mn is a multiple of 12, but neither m nor n is a multiple of 12. So that's the interesting case we need to investigate. So that's what led us to conjecture you can't tile this 66 by 62 with 12 by 1s. Okay, you can go to the next. Okay. Okay. Now we define a coloring or numbering of the rectangles homogeneous if each color occurs in the same the same number of times. In this case, we use numbers, so you can just say each number occurs the same number of times. So for example, in a numbering, if number 1 appears the same number of times as number 2, and so on up to the number 12, then that's a homogeneous numbering / coloring. Okay, so you can go to the next. Yeah. So now is the interesting part where we can break the 62 by 66 rectangle into 4 smaller rectangles. So we've got a 60 by 60 here, and a 60 by 2 here, and a 6 by 60 here, and a 6 by 2 here. Okay. So what we can do is, remember, if we go back to our numbering from earlier, if one side of a rectangle has a side divisible by 12, what it means is, if you look at the first row, remember you're starting at some number and you're looping backwards or forwards. In this case, looping backwards, going right. So we loop backwards and go through all the numbers from 1 to 12. But since you have a multiple of 12 as the number of squares in each row, you're going to have every number from 1 to 12, you're going to have every number m times. So every number from 1 to 12 appears m times in the first row. And similarly, the same thing will happen in all the other rows. So what it means is, if you have one side of a rectangle divisible by 12, every number will appear the same number of times. So any rectangle of this form will be a homogeneous rectangle. Okay, so wait, we go back to previous slide. Okay, yes, thanks. Okay, so 60 by 60 and 6 by 2 and 6 by 60. So number 60 is divisible by 12. So all these rectangles are homogeneous. So because each subrectangle has a dimension that is a multiple of 12. And so you can also note that if you consider all these cells combined in these 3 subrectangles, if you add this all together, the number of numbers, each number will still appear the same number of times, because each number appears the same number of times here and over here. So if you consider all the cells combined, there's combined cells, every number appears the same number of times. Okay, so I can go to the next. Okay, but now if you look at the 6 by 12 subrectangle, that's the final subrectangle. will be colored like this. So if you go through the coloring, you'll eventually see that this bottom right 6x2 rectangle, it will have 1, 2, 3, 4, 5, 6, and then 12, 1, 2, 3, 4, 5. Okay, and the issue is this is not a homogeneous rectangle because the number 1 appears twice and the number 12 only appears once. So now, since we had 3 homogeneous rectangles and this final rectangle is not homogeneous, it means that it's combined, the entire 66 by 62 is not homogeneous because remember, so this whole region here had the same number of every number, but this last region here didn't have the same number of every number. So the entire rectangle is not homogeneous. Okay, so the issue with this is, remember, if you look at the coloring, it turns out that if you put any 12 by 1 rectangle anywhere in the grid, so no matter how you orient it or put it in the grid, it's going to cover every single number exactly once. So for example, we might have 3, 4, 5, and so on until it goes back to 2 here. So they'll cover every 12 by 1 covers every number exactly once. So if we assume you could tile the entire rectangle with these 12 by 1s, it means that every number is going to appear the same number of times, which means it's homogeneous. However, we proved it's not homogeneous. So we get our contradiction. So we can just go to the next slides. So yeah, show what the contradiction is, to summarize what's going on. Yeah, so a larger rectangle is not homogeneous, and that's what makes tiling impossible. So yeah, we're done.
So Yasiru, what would you say are the transformation and the invariant here?
All right. So the invariant, I'd say, is whenever you place a 12 by 1 rectangle on the entire grid, the number of times each number appears is going to be all the same. So when you keep on adding new 12 by 1 rectangles, the invariant is that every no matter always every number appears the same number of times. The transformation, you could say, is when you adding each tile 1 by 1.
Great, thank you. Did anybody have any questions about that one? Cool. Gordon, did you want to take this one?
Yeah. So I think this question is a bit intuitive. So maybe I'll just give everyone 1 or 2 minutes to think about it before I start going over it.
Cool.
So I guess just to give out a hint, one thing that you can do is you look at the minutes. So it is in fact a multiple of 3. So you can think about what happens after every 3 minutes. I guess we'll get started. So as I just said, we will be looking at the room after every 3 minutes. So each minute, either 1 person enters or 2 people leave. So let's say we have n people in the room initially. After a minute, there will either be n plus 1 people or n minus 2 people, right? And if we look at every 3 minutes, you can either have +1, +1, +1, or +1, +1, -2. And just give a few other examples like +1, -2, -2. And if you just have +1, -2, +1, it will be exactly the same as the second scenario. So if you look at all of these different combinations of people entering and leaving, you can see that all of them are kind of similar, right? They're all they're all equal to 0, mod 3. Right? And I guess, and then this is the invariance in this question. So for every 3 minutes, the number of people in the room does not change when you considering the number mod 3. So if we're starting with zero people in the room, then you know that after some multiple of 3 minutes, the number of people in the room should also be 0 mod 3. Right, so if we can get some dot points on the screen. I gotta remove all of it, clear. Yep. Yep, so as what I said, there'll either be n+1 or n-2 people. The difference between those two possible outcomes is 3. And can we get some more dot points? Just 2 more, I think. Yep, so at any time t, any 2 possible n values differ by a multiple of 3. And since 3 to the power of 1999 is a multiple of 3, therefore, can we get all the 2 more dot points? Yep. So as I said, because 3 to the power of 1999 is a multiple of 3, and we started with the room being empty, which means there's no person in it, the number of people in the room after 3 to the power of 1999 minutes should be 0 mod 3, right? But the question is asking, could the room contain 3 to the power of 1000 plus 2 people, which is not possible because that is equal to 2. That's congruent to 2 mod 3. And therefore, we can conclude that it cannot contain 3 to the power of 1000 plus 2 people after exactly 3 to the power of 1999 minutes. And yeah, that's basically it. Yeah, so the invariance will be the number of people mod 3. Like that's that does not change every 3 minutes, and we can use that to solve other questions of similar type as well.
And I think, like in this case, the transformation is not just adding a person or taking 2 people away. It's doing that 3 times. And there's also there's different options at each step of the transformation. So yeah, the invariance principle works when you have more than one possible transformation that you can apply.
Yeah, because they're all congruent to 0 mod 3.
Cool. Okay, so let's have a look at example. We've got a bubble chamber, and there's 3 different types of subatomic particles. You have 10 particles of type X, 11 particles of type Y, and 111 particles of type Z. So we've got some collisions between the particles. So if an X and Y collide, they'll disappear and become a Z. If Y and Z collide, they'll disappear and become an X. And if an X and Z collide, they'll disappear to become a Y. The question is, can you have a lot of collisions so that eventually only one type is present. All right. So let's you can go to next dot point. Yeah.
Do we want to give people some time to work on it first?
Oh yeah, give some time to work on it. Yeah.
Are there any hints you think people should have?
All right. Hint could be examine the relationship between number of particles of x and y and z. So try a lot of different combinations of collisions and try to see the relationship between x, y, and z each time you do it.
All right. I think we'll give people about 2 minutes for that.
Oh yeah, another nice thing to do is make the numbers smaller again, so do some smaller cases. For example, you could have, instead of 10 and 111, you could do start with a simple case such as 3, 4, 5 for x, y, and z, and then see all the possible combinations of the number of each particle you can have, and yeah, you can try to see if there's a pattern or again an invariant. So an invariant could be something that's always true for any possible combinations of the x's and y's and z's.
Hopefully you've had some time to think about that one.
Okay. Okay, yeah, you can move on to the next slide to see an example of oh yeah, and the one after that as well. Oh yeah, next one. Yeah, okay. So we've got 10. So we start with 10, 11, and 111. So then we can experiment different combinations of collisions and see what we get. So if we collide x and y together, the number of x's goes down by 1, the number of y's goes down by 1, and the number of z's goes up by 2, because the x and y will turn into 2 z particles. And let's say we do collide x and y again, the number of x's goes down by 1, and the number of y's goes down by 1, and the number of z's will go up by 2. So now we could try a different combination. So we're going to collide x and z. The number of x's will go down by 1 to 7. Number of z's will go down by 1 to get 114, and the number of y's will go up by 2. So go from 9 to 11. Okay. So since we're kind of shifting between x, y's, and z's, so since we're transforming x and y into a z, for example, or a y and z into 2 x's, since we're shifting between the x, y's, and z's, we could consider the differences between the number of x, y's, and z's. So, for example, we could examine the difference between z and y. So, initially, z minus y is 100. But now, after you do the x plus y step, remember your y's goes down by 1 and your z's goes up by 2. So the net change will be 3. So you'll go up by 3 there. So 103 now is the difference between z and y. And we're doing the x plus y step again. So number of y's goes down by 1 and the number of z's goes up by 2. So z minus y will increase by 3. So 106 will be the new value. And now we're doing x plus z. So the number of z's goes down by 1 and the number of y's goes up by 2. So z minus y is going to decrease by 3 again and go down to 103. And you can also look at y minus x. So y minus x here is 1, and y minus x here is 1. Y minus x here is 1, and but over here, y minus x is 4. So what do we see about these numbers? So we can see 100, 103, 106. So you're going up by 3 each time, and you're going down by 3 over here. And over here, you have 3 1s, and you're going up by 3 to get to 4. So using this, you could hypothesize that z minus y and y minus x and z minus x are all invariant modulo 3. So what it means is z minus y is always going to be some fixed number plus a multiple of 3. So over here, z minus y is going to be 1 plus a multiple of 3. So for example, 1 plus 99 is 100, and 1 plus 102 is 103, and so on. So you can also do more combinations of x, y, and z collisions, and if you get more and more data, you can make your hypothesis stronger, or your confidence that the hypothesis is correct. So be more confident if you do more test cases. Okay, so we can go to the next dot point. Okay. All right, so now we're going to do the general case to prove this invariant is true. So general case is we can just label a number of x's and y's and z's as a lowercase x, y's, and z's. So now in this general case, if you collide x and y, so number of x's goes down by 1, and number of y's goes down by 1, and number of z's goes up by 2. Now we can look at z minus x. So z minus x. So z minus x and z minus y are going to increase by 3. If you look at y minus x, so y minus x, so this minus this is the same as this minus this. So these will be constant. So again, you can see that the hypothesis is correct in this case when you apply the x and y collision, because all the 3 differences are going to be the same modulo 3. Now you can use a symmetry argument, because what you see is this entire problem is symmetrical in x, y, and z, because so remember, x and y's give you 2 z's, y's and z's give you 2 x's, and x and z's give you 2 y's. So you can actually use the exact same argument for the y and z collision and the z and x collision. So that could help speed up your solution. But yeah, you should be careful to identify that there is symmetry present. We could still go through the last next 2 cases as well, just to see how they're similar. So you can go to the next dot point. Oh wait. Okay. The similarly is over here. Yeah, I didn't see that before, but yeah. So using symmetry, you can similarly prove that z minus x and z minus y and y minus x are going to be constant modulo 3. So that will prove our invariant. So yeah, now we can go to next dot point.
And I think like usually if you have that kind of symmetry where you're just doing the same argument 3 times, usually if it's obvious, you can just write similarly for the other 2 cases.
Yeah. Okay, yeah, but yeah, it should be still be careful to make sure it indeed is symmetrical, because for example, let's say a case where it's not symmetrical, say I had 4 things, and this is maybe an example of something that's almost, it may look symmetrical, but it's not. So for example, you had say X and Y is giving you Z, Y's and Z's giving you W's, Z's and W's giving you X, and W and X giving you Y. It actually turns out not to be symmetrical. It's actually called cyclic, where you can, there's a symmetry where it cycles around, but symmetrical is a stronger condition, which means the problem behaves the same way when you switch any 2 of these X, Y's, and Z's and W's. But cyclic is when the problem, when the situation remains the same when you just shift these cyclically. So for example, if you had Y, Z, W, X, so this is called cyclic, and that's a weaker version of symmetric. Okay, so that's a side note. So yeah, you should be careful when you look for symmetry in questions. Okay, so I can see in the initial case, 10, 11, and 111. You see initially Y minus X is 1, so that's not 0 modulo 3. And remember, we have an invariant, so the invariant is Y minus X will always be 1 modulo 3. So initially it was 1 mod 3, and since the invariant applies, no matter how many moves or collisions happen, Y minus X will always be 1 modulo 3. So it means that Y minus X cannot be equal to 0, so X and Y populations can never be the same. Okay, so you can go to the next dot point, and we get a similar conclusion for the other 2, for Y and Z and X. So you have a similar argument where, so since X and Y can't have the same number of particles, you can't have only Z's, because if you had only Z's, then you have 0 X's and 0 Y's, but you can't have X and Y's being the same. So you can't have everything being Z. And using a similar argument, you can't have everything being Y and can't have everything being X. That's so that should be, yes, that's the end of the solution. So summary of this solution would be, first is you would play around with these collisions and trying to see what numbers you can get, and also doing some small cases, make it easy to spot patterns. And next step would be to identify the invariant, which is looking at the difference between the number of X and Y's and Y's and Z's and Z's and X's, and seeing the modulo 3 invariant. And then you can use you can prove the invariant, and you can look at the starting conditions of the invariant. So you can see what initially the value of the invariants are, and using the initial values of that invariant, you know, the final values of the invariant will be the same as the initial values, and then you can prove that this final state is impossible because it doesn't give you that the final values of the invariant are the same as the initial values. So that's, yeah, it's how.
If anyone has any questions about that, just post them in the chat. It seems like we've kind of subtly used 2 different invariants here. There's the obvious transformation of the collisions, but there's also the fact that we could cycle and swap the variables. So we're introducing kind of a symmetry into the argument. And you will have seen earlier with some of the geometric questions that invariance and symmetry are related somehow. So a symmetry is just something that keeps something else invariant. Cool. Gordon, did you want to take this question?
I think it's Yasser's.
Oh yeah, I think I'm doing this question. Yeah. All right. So this is a number theory question that again uses invariant techniques. So we have a set of 1,985 positive integers. So not necessarily distinct. So some of them can be equal. All right. So this is not necessarily distinct. So it's not quite a set by its usual definition, because you can have repeated elements, and these positive integers, none of the integers have prime factors greater than 23. So the question is, prove there exists 4 integers in this set whose product is equal to the 4th power of an integer. So can we find 4 integers no matter what the set of 1,985 integers is? Can you always find 4 integers whose product is something to the power of 4? All right. So again, I give everyone a few minutes. Think about the question. Some maybe ideas you can think of are. Let's instead of 4th power, let's start with perfects. Looking at perfect squares before looking at perfect 4th powers. So remember that for an integer to be a perfect square, all the exponents of the prime factors must be even. So then that's the only way you can have a square number, because so in your prime factorization, if all the exponents are even. And again, for a positive integer to be a 4th power, all the exponents in the prime factorization have to be a multiple of 4. So you can equivalently phrase this question as trying to find 4 integers, and when you multiply them together, all the exponents in your prime factorization will be multiple of 4. So you could have a few minutes to think about this question and see what you can do with those exponents of prime factorizations.
I think because this is a number theory kind of question, we might give people about 5 minutes to work on it, just because it's probably more technically involved.
Yeah, okay. So maybe some more hints are, you can do an example of 2 squared times 8. Let's see if I can use the text. Oh, wait. Okay, let's say an example is 2 squared times 3 cubed. Actually, no, I won't use text. So yeah, I'll just write it. So 2 squared times 3 to the 5 times 7 to the 8. And let's say, so that's one number. And the second number, let's say, is 2 to the 4 times 3 times 5 squared times 11 to the 4. So if you look at these two numbers, you see the exponents of 2 are 2 and 4, and 2 and 4 are both even, so 2 plus 4 is even. And also the exponents of 3 are 5 and 1. 5 and 1 are both odd. 5 plus 1 is 6, and 6 is even. So what you can see is, if we take a prime factor in two different numbers, and if the exponents have the same parity, then when you multiply the two numbers together, the exponent, the combined exponent of the prime factorization of the product will be even. You can try to analyze the parity of each exponent in the prime factorization. That's another hint you can think about.
All right, hopefully everyone's had some time to work on that and think about it.
All right, so we can, we can start going through the solution. All right, so we can go to the next dot point. Okay, so go to the next. Okay, I think might be having some technical issues, but let's see. Okay. Okay, so each number has prime factors that are all at most 23. So you can write the numbers as 2 to the power of some times 5 to the power of some number f3, and so on, up to 23 times to the power of f9. And all your exponents are going to be positive integers. Actually, they could in fact be non-negative integers as well, because they don't have to be divisible by 12. They don't have to be divisible by 2. For example, you can have an exponent of 0 as well. Okay. So we can look at define this function g of n. So that just tells you the parity of each of these f's when you divide by 2. So parity is useful because that can help us determine if some number, if you multiply numbers together, you get a perfect square or not. So the gn is going to be 1 if your fn is 1 mod 2, and g of n is 0 if your fn is 0 mod 2. So if you multiply two different numbers in your set together, if the two g values match, if you add, that means you add two numbers that are the same mod 2. You'll always get 0 mod 2. So your exponent will be even. So if all the exponents are even, you'll get a perfect square. Yeah, so you can go to the next dot point. Okay. So if you look at numbers F1, F2 up to F9, if you look at these numbers, there's two ways of choosing the parity of F1. There's two ways of two possible combinations of the parity of F2 and so on. And there's two ways of two possible parities of F9. So total number of possible combinations of parities of all these Fs will be multiplying 2 by 2 and so on up to 9 times. So as 2 to the 9 equals 512 possible combinations of parities. Okay. So now we have something interesting, which is the Pigeonhole Principle. Okay. So let's take 1472 of these integers. And it turns out that you can put them into 736 pairs. They have A1, B1, A2, B2, and so on, and A736 and B736. So that every pair contains two numbers with identical 9 tuples of exponent parity. So what's going on here is we've got 1985 numbers, and it's 512 different combinations of 9 tuples. So since 1985 is a lot more than 512, you can find two numbers, A1 and A2. You find two numbers, A1 and A2, with the same combination of parities. Okay, it should be B1. So A1 and B1. And now you can delete these two numbers, A1 and B1. And now there'll be 1983 numbers left over. And now you can consider the remaining 1983 numbers. Again, you can use a pigeonhole principle. Two of them will have the same combination of parities. So A2, B2 have the same combination of parities. Now you can delete all four of these numbers. You have 1981 numbers left. And again, use the pigeonhole principle. 1981 is more than 512. So again, you can find two numbers with the same combination of parities, A3, B3. Okay, and now you can actually continue this process. You can find your pairs and delete them, and then use the pigeonhole principle to get a new pair. So this is going to work until you have if you have 513 numbers left over. 513 numbers left over. That's the last time you can apply the pigeonhole principle. So after that, you can't apply it anymore. In fact, so when there's 511 numbers left, that's when you can't apply the pigeonhole principle any longer. So the total number of numbers you can put into pairs will be 1985, 5 minus 511, and divided by 2. So the number of pairs in total will be 1472. Wait, hang on. Should be, there's 1472, so yeah, it should actually be, yeah, it should be 513. Okay, so 185 minus 513 and divided by 2 is the total number of pairs you can do. And if you look at these 736 pairs, so all of them, both numbers in every pair have the same 9 tuples of parities. So F1, F2 up to F9. Okay, so this argument is quite subtle because we're applying the pigeonhole principle multiple times, and as you go, you're deleting numbers from a set of pigeons. So you got 185 pigeons, and you're deleting 2 pigeons each time you apply the pigeonhole principle. All right, so that's how you get your 1472 numbers in pairs. Okay, so yeah, you can go to the next slide. Okay, so remember from earlier, if all the numbers, if 2 numbers in a pair have the same parities of exponents of their prime factorizations, when you multiply them together, all the parities will add up to an even number. So the product of numbers in each pair is a perfect square. So kind of halfway done, because we found lots of different ways of multiplying 2 numbers to get perfect square. The challenge is to find a way to make the product of some 2 numbers equal to 4th power. So that might take a little bit more effort than proving perfect squares. All right, so we can go to the next stop point. Okay, so if you let Ci, okay, so if you multiply the 2 numbers in each pair together to get Ci, so you get 736 different values of Ci. Remember that all the Ci's are perfect squares. So you can take the square root of these perfect squares. And remember, all the numbers, their prime factors are at most 23. And if you multiply 2 numbers in pairs together and take the square root, still the prime factors of all numbers will be at most 23. So you won't get any extra prime factors. Okay, so you can go to the next stop point. Now we can apply the pigeonhole principle again with these numbers. So again, 736 is greater than 512. So if you remember the 9 tuples of your parities of your exponents, since 736 is greater than 512, there'll be 2 numbers, some 2 numbers, which have the same 9 tuple of exponent parity. So we're using a similar argument again. All right, so go to the next. Yeah. What we have is one of these square root CKs times another square root of CJ. When you multiply them together, you'll get a square number. So you get an n squared. So you can choose a CK and a CJ. So the square root of CK times the square root of CJ will equal a square number. Okay, so go to the next dot point. Now we can square both sides. So n to the power 4 is CK times CJ. But remember that that's each of the C's are a product of 2 of the original numbers in the set. So CK is AK, BK, and CJ is AJ, BJ. So we have found 4 numbers whose product is a 4th power. That's we are done. So we can recap this proof. So the first thing we did was look at the fact that for a number to be a perfect square, all its exponents in its prime factorization have to be even. And for a number, for product of two numbers to equal a perfect square, for each prime factor, the parity of the exponent in A has to equal the parity of the exponent in B. So the two parities of the exponents have to match in for each prime factor. All right. And so the next thing is, so now we can simplify the problem. So instead of trying to figure out whether a number is perfect square or not, you can just look at the parity of the exponents in prime factorization. And you can also list out all the 9 tuples of possible parities of your prime factorization for prime factors at most 23. So now it's pretty good because we brought an infinite number of possible cases and we've grouped them into different classes. So the different classes are your different parities of your exponents. So even though there's infinite possible exponents, infinite possible values of exponents, there's only finite possible parities of the exponents. The parities are the main thing that matters in this question. Next thing we did was repeatedly use a pigeonhole principle to find 736 pairs of numbers whose product of each pair is a perfect square. And so that again uses, so the pigeonholes in that case would be the 512 different parities of exponents. And then we can take all the products of numbers in the pairs, so those are your C's, and take the square root. And again, you can use the pigeonhole principle to get square root of something times the square root of something equals a perfect square. And if you square both sides and replace the C's with the corresponding AKs and BJs, you'll eventually get a power of 4 is a product of some 4 numbers in the set. So yeah, we found 4 numbers whose product is a 4th power. So that concludes the proof.
What would you say is the invariant here, Yasiru?
All right. This is, let's see. I thought this question was more of a pigeonhole principle type of question, but invariant could be the fact that perfect squares, all the exponents in the prime factorization has to be even. So no matter what the perfect square is, it's a necessary and sufficient condition for all the exponents prime factorization to be even. So that does help narrow down the cases because you just have to look at the parity of the exponents. So that's the main thing that matters. So the actual the actual size of the exponent is not too important, but it's just the modulo value, the value modulo to them is important.
Yeah, so I guess you could say perfect squareness is invariant with respect to transformations that keep the exponents the same mod 2.
Oh yeah. Yeah, so if you multiply 2 perfect squares, for example, you get a perfect square. So although we didn't exactly use that fact in this question, but I did use the fact that the parities add when you multiply 2 numbers and look at the exponents.
Cool. Does anybody have any questions about that one? Alrighty. Gordon, did you want to cover this question?
Yeah. Yeah, sorry, can you please clean the screen first? Or can I do it? Oh, yeah. Oh, thank you. So 4 congruent right triangles are given. One can cut one of them along the attitude and repeat the operation several times with the newly obtained triangles. Prove that no matter how we perform the cuts, we will always find among the triangles 2 that are congruent. So this question is actually really interesting because we're actually making our own invariant instead of using something that's from the question. So I guess I can give you guys like around 1 to 2 minutes to think about it, of how you will start on the question. Just to give some hints, you guys can probably look at, you can like actually try to visualize on cutting the triangles and see the similarities between your newly obtained triangles and your original one. All right, I guess that's enough time. Can I get 1 dot point? All right, so to start, without loss of generality, we may assume that the length of the hypotenuse is 1 and the legs are of lengths P and Q. So I'll just draw it real quick. Draw it here. So this is one of the triangles. So you have hypotenuse 1 and length leg P and Q, just to visualize. So in the process of cutting, the new triangles will be in the ratios PM, P to the power of M, times P to Q to the power of Q to the power of N, to the original ones. So for some, I think it's actually positive instead of negative. Actually, I think it's non-negative instead of negative. That's a typo. Anyways, so when we're cutting it along its altitude. Will be here. So as we can observe, these 2 new triangles are actually similar to the original triangle. So you know the length of the new legs will be in the precise ratio of PQ to your original triangle. So let's call that pair MN. Can I get another dot point? Yep, so every time we cut a triangle, we replace the pair MN. So in this case, let's take our original triangle. For the original one, MN will be 0, 0. And if we cut it, we'll get 1, 0 and 0, 1 as our ratio. So we'll have, let me just think. Let's clear that. Can I get another dot point? So this is the interesting bit. So we will assign the weight 1 over 2 to the power of n plus n to the pair m comma n. And therefore, when you're cutting the triangles up, your new weight will be 1 to the power of 2 m plus 1 plus n plus 1 over 2 to the power of m plus 1 which will still equal to 2 to the power of n plus n. This is our invariant of the question, right? The sum of all the weights will always be this number times 4, because originally there were 4 congruent right angle triangles. Can I get another dot point? Yep, so initial value will be when m and n are both 0. So 1 on 2 to the power of 0 is 1. So because there were 4 triangles, the initial value of I will be 4. And then we just proved that it doesn't matter how you cut the triangles, your I value will always be 4. And let's consider this sigma function, right? This one. So what that represents is all the possible triangles that you can possibly get. How would I explain it? So that is basically the sum of weights of all the triangles you can possibly get if none of them were pairwise congruent. And because you can see, how do I explain this? Yeah, because for different m and n values, you will get different triangles. And this value, if you compute this value, you'll get 4. But because we cannot possibly cut infinitely, your value of I will be strictly less than 4, because there are some triangles, like you cannot possibly get all the triangles. And that is a contradiction, because we started with an I value of 4. And at the end, if at some stage the triangles were pairwise incongruent, we'll get an I value less than 4. And that contradicted our initial value. And therefore we proved that you will always have 2 congruent triangles after cutting.
Great, thank you.
I guess that was a bit confusing, but if you guys have any questions, feel free to leave a message.
Cool. All right, so now we'll move on to semi-invariants, which are kind of a generalization of invariants. And it's, rather than talking about the function of the setup staying the same, we're saying that it only increases in the same direction when you apply the transformation, or it decreases in the same direction. And this can kind of be an abstract increasing or decreasing. This order relation here doesn't necessarily have to be the standard ordering on the real numbers. It could be, for example, a divisibility relationship or something like that. You can certainly make arguments of that form, but you would need to explain why those are working as you write the solution out. So it can be either strictly or non-strictly increasing if you're using the standard ordering on the real numbers. And a key observation to make here is that if you're saying that the transformation always increases, always decreases, let's say, the monovariant, then if you know that the monovariant of A is greater than the monovariant of B, then you can't get A by transforming B, because transforming B can only decrease it, whereas A is bigger. Does anybody have any conceptual questions about that explanation? Cool. All right, so we'll do one example for semi-invariants, and then we'll wrap up. So if we have n markers on a table with one side white and one side black, and we transform them according to these rules, then we want to show that we can only reach a configuration with 2 markers left if and only if n minus 1 is not divisible by 3. So we'll give you a few minutes to think about this one. Let's say about 3 minutes. Sorry, just a correction. I think this may be an invariance problem rather than a monovariance problem. And in that case, we don't actually have an example for monovariance. So please ask any questions if you're at all confused about that one. And we'll definitely put some problems on that in the problem set. Cool. Has anybody got anything that they want to share? Otherwise, we can jump straight into it. Cool. So obviously we have either white or black markers, white and black sides of the markers, and one of the sides has to be up. So we'll talk about the markers in terms of which side is currently up. And if we take an example of this, so at every step, we want to choose a marker with the white side up that's not on the outside. So we can't choose this one because it's on the outermost edges of the row. And we can't choose this one because it's not white. So we have to choose this one in this case. And we want to get rid of it and reverse the 2 next to it. Reverse their colors. So we'll end up with these white ones here. And you'll notice that we had 2 black markers before, and now we have 0. And in fact, the number of black markers always has to remain unchanged in terms of parity. And the reason for that is because if you have black and then white and then white, and you pick this one, these 2 will swap colors. So you'll have the same number of black markers because you'll lose a black marker here and gain a black marker here. If they're both white, then you'll get 2 black markers. And if they're both black, then you'll lose 2 black markers. So the parity has to stay the same. And that's why it's important that we have the restriction that the marker we remove is not only white, but it has to be on the inside, because it has to have a marker to the left and to the right for that invariance to hold. If we only have two markers left, then we're saying they have to be the same color. And this is only the case if n starts bigger than 2. Obviously, if n is 2, we can make them whatever we want. But if n begins at 3, for example, so here's an example of n equals 3. We can remove this white marker, flip these two, sorry, I lost my way a little bit with this proof. But we can go on, we can define an invariant here. And so we'll give each white marker an invariant, which is just -1 if the number of black markers to the left is odd, and +1 if the number of black markers to the left is even. Yes. So our invariant of the whole configuration, if you sum up those numbers that we give to the white markers, it should be invariant mod 3. And you can check that because when you flip a white marker, you change the values to the left of it, and you change the values to the right of it. And so just algebraically and arithmetically, you can show that that's an invariant. And here we're breaking it down into the 3 cases where you have both the same color, so both black, both white, or different colors. And of course, there's 3 possible values for the invariant. So the only if component of this proof is just by applying this principle invariance here. Whereas the other way around, you can't just use the invariance, you also have to do some extra work to show what the transformation actually is. So if we end up with 2 black markers, then obviously the invariant is 0 just by calculation. And that means that all the previous states have to have had S being a multiple of 3. If it ends with 2 white markers, then we have S is 2. And so if we're ending with 2 white markers, then we can't have n-1 being divisible by 3. So if we start with at least 5 white markers, then we're saying that n has to be either 0 or 2 mod 3. It can't be 1 mod 3. Because otherwise we would end up with no markers. Yeah, so if we want to end up with 2 markers left, then we can't have n being 1 mod 3. Because yeah, so if we're starting with n is at least 5 white markers, then we need 0 or 2 mod 3 white markers, because of the invariant. So if we take 3 different moods in succession, on the 3 leftmost white markers in the configuration, so if we have at least 5 markers, at least 5 white markers, then we can remove these 3 in succession, the leftmost 3 in the configuration. There could be other stuff over here. But if we remove these 3, well, these will switch. But this one will get switched twice. So we'll end up removing just 3 white markers from the configuration, and this white marker here will become a black marker, and this white marker here will become a black marker, and these 2 will stay the same. So if we look at the end case where we have 2 white markers left, two markers left, then sorry, if we start with this configuration of n is greater than 5 white markers, and we take away 3 each time, we know that n is 0 or 2 mod 3, and we're taking away 3 each time. So in the end, we have to have 0 or 2 mod 3 white markers, which is just 2 or 3 once we reduce to the smallest case we can get. And if we just have 3 white markers, we can take out the middle one. Assuming we've reduced it to the smallest, to the simplest case with 3 white markers, we can take out the middle one, and the other 2 turn black. So point 7 is the only if component of the proof, and point 8 is the if component of the proof. So point 7 has to use the invariants, whereas point 8 does use the invariants to see roughly what we should do, but it has to explicitly construct the transformation that gets us there. Does anyone have any questions about that problem? It's a little bit in depth, and we'll post these slides up so you can take a closer look at that in your own time. But that's all the content we have for this week, unless anybody wanted to ask about the problem set from last time. I'll also post in the chat a feedback form, which you guys can fill out. And we won't be having any workshops until next term, I think. So yeah, if you can keep your feedback specific to this. So S is the sum of, so for each white marker, we look at the number of black markers to the left, and it's either -1 or 1. We score it either -1 or 1, depending on whether the number of black markers to the left is even or odd. And then we just sum over all the white markers to get S. Cool. Does that answer your question? Great. Yeah, if you can fill out the feedback form, that would be very helpful in terms of content and presentation for next term. Other than that, see you in the next workshop. Thanks for coming, everyone.